Hi, my name is Arvind Narayanan. In this talk, Xumiao and I will introduce our work titled A Variegated Look at 5G in the Wild, Performance, Power, and QoE Implications. This work was jointly done with many of my colleagues and collaborators from the University of Minnesota and the University of Michigan. Commercial 5G has been around for over 2 years, and operators are continuously expanding and upgrading their 5G deployment. Reports suggest that 5G adoption is going to hit 1 billion by next year. This is not surprising given the hype 5G enjoys as well as the exciting use cases promised by it. However, there exists a vacuum in understanding how 5G as a technology performs out in the wild. For instance, little is known about the power characteristics of 5G. Is it more energy efficient than its predecessor 4G or LTE? Are there any trade-offs? What about 5G's network performance footprint? 5G ecosystem is continuously evolving, with different deployment strategies such as non-standalone or NSA 5G, which relies on LTE for control plane operations, and standalone 5G, both of which are here to stay. Coupled with the low, mid, and high band frequency ranges, the 5G ecosystem has become complex to understand. Therefore, we also seek to improve our understanding of 5G's network performance and identify potential issues. Lastly, it's unclear how 5G will impact application quality of experience or QoE, and what could application developers potentially do to leverage 5G technology. To answer these questions, we build a holistic testbed consisting of different 5G smartphone models, external power monitors, etc. Using multiple 5G carriers, we carry out extensive in-field experiments in 2 US cities and conduct a comprehensive measurement study. We have released the dataset and measurement tools. We begin by first talking about the end-to-end network performance. A typical end-to-end path includes the end user or UE connected to the carrier's base station, which is then connected to the carrier's core. The core further acts as the gateway to the internet. Prior work has typically deployed virtual machines in public and private clouds to conduct end-to-end network performance tests. However, due to the known ultra-high bandwidth capacity of 5G, the internet can become a bottleneck affecting our experiments. Our goal was to understand the network performance provided by the carrier's infrastructure in different 5G deployments and settings. But academic researchers like us do not have visibility into the mobile carrier's infrastructure and the policies enforced by them. To overcome these challenges, we take the following approach. Ookla's speed test service is a popular tool for testing network performance. All 5G carriers in our study hosted their servers on Ookla's speed test service. For example, as shown here, Verizon hosts around 48 servers in the US, which are typically located in major metropolitan cities. We leverage the flexibility of server selection provided by Ookla, as well as the carrier's presence, to reduce if not eliminate the impact of internet-side bottlenecks. First, we look at the latency characteristics of Verizon's millimeter wave 5G. With the UE's location fixed in Minneapolis, we measure the latency across all their servers in the US. When tested with the closest server located in Minneapolis itself, we observe lowest latency of just 6 milliseconds. The latency increases by over 2 times when tested with the second closest Verizon server located in South Dakota. Going to either coast increases the latency by a factor of approximately 10 times. We also conduct similar experiments on Verizon's low-band 5G and LTE network. Due to the flexibility in frame structure and control over the transmission time interval or TTI in 5G NR, both low-band and millimeter wave 5G exhibits better round-trip times than LTE. Nonetheless, our results clearly quantifies the importance of edge. We conduct similar experiments to measure throughput over millimeter wave. With multiple connections, the UE can achieve an impressive downlink throughput of over 3 Gbps across all the servers in the US. However, with a single TCP connection, even after tuning TCP parameters, we find that the downlink throughput degrades as the distance between the user and the server increases. These results again signifies the importance of edge, especially for bandwidth-hungry applications. It also highlights the issues that exist today with current TCP layer mechanisms. The uplink throughput, on the other hand, peaked at around 220 Mbps. Both single and multiple connection tests can achieve peak performance across all the servers in the US. Such uplink performance could very soon enable video broadcasting at 4K and beyond resolutions. Our study also finds that it's not just the number of connections or TCP protocol. Performance bottleneck can also shift to factors at end devices. On the UE side, we find that support of higher levels of carrier aggregation scheme significantly boosts throughput performance. On the server side, we find network configuration and limitations of the infrastructure itself can be a reason for performance degradation. To demonstrate this, we select all the speed test servers located in the state of Minnesota and conduct speed test measurements. No doubt, using the carrier's own server provides the best throughput of over 3 Gbps. Moving to other non-carrier based servers suffers a 10% degradation in throughput. This is most likely due to the additional internet side overheads. Moving on, after several repeated tests, our results find that production level speed test servers might not support throughput over certain limits even if the UE can. For example, as annotated in the plot, certain servers are bound by their uplink capacity of 1 Gbps. We believe such bounds might either be due to NIC side or switch side port limitations or network configurations. In either case, with millimeter wave's ultra-high throughput capacity, one needs to ensure servers can fulfill uplink or downlink throughput requirements of the applications. This can be challenging due to increase in costs coupled with infrastructure limitations. We also evaluated network performance of T-Mobile's low-band 5G service, which is deployed in both standalone and non-standalone modes. From the latency perspective, non-standalone 5G shows marginally better round-trip times than standalone 5G. On the throughput side, we find that both downlink and uplink performance of standalone 5G can achieve only half of what non-standalone 5G can deliver, suggesting commercial standalone 5G's network performance as of today is worse than that of NSA. We believe this to be due to either carrier aggregation not yet supported for the standalone modes or that the 5G core itself is not fully mature. We also conducted a preliminary study comparing the number of handoff events between standalone and non-standalone 5G. We selected a 10-kilometer route which traversed via busy downtown regions and freeways. We configure the UE in one of the 4 settings and monitor the handoff activity. In the first setting, we only enable the standalone 5G band. Color of the horizontal bar shows the type of radio active, while the vertical ticks indicate the type of handoff. In this case, since only the 5G band was active, the whole bar is green, and the black ticks indicate the horizontal handoffs. Horizontal handoffs here indicate change in base station or tower. We observe that the UE experiences a total of 13 handoffs for the 10-kilometer route. In the second setting, we enable both NSA 5G bands as well as LTE bands. In this setting, the UE experiences a total of 110 handoffs, which is also including 90 vertical handoffs. Vertical handoffs here indicates change in data transmission technology. Third, we enable just the LTE bands and disable all 5G bands, mimicking a traditional LTE-based user. And in the final setting, we enable all the bands. This is also the default setting set by the carrier's firmware on UE. Compared to all the settings, clearly standalone 5G experiences far fewer handoffs. Well, the number of handoff events not only has performance implications on application, but also leads to additional signaling and scheduling overheads, which has cascading effects on energy consumption. Nonetheless, comparatively speaking, our preliminary analysis suggests reduced control plane signaling and scheduling overheads using standalone 5G. A more detailed study on this front is part of our ongoing work. Next, Xumiao will talk about the power characteristics of 5G.
Hi, I'm Xumiao Zhang. Now, let's take a closer look at the power characteristics of 5G. We first look into RRC power management and study how the transitions between different states affect power consumption. Then, we study the impacting factors of power during data transfer, such as throughput and signal strength. We compare with the latest 4G results. To better model the UE's power consumption, we use a machine learning-based data-driven approach for power model construction, considering multiple factors. We build power models for different devices, networks, and radio technologies. Lastly, Since it is inconvenient to carry hardware power monitor for power measurements, we benchmark and calibrate software-based power monitoring solutions used by prior work. We first investigate the 4G, 5G RRC system machine. RRC, or Radio Resource Control in cellular networks, is a power management protocol. In 4G and non-standalone 5G, there are two main states, connected and idle. In the connected state, UE actively monitors the radio for incoming data. The idle state is a low power state where UE only periodically wakes up. UE transitions between different states to balance network performance and power consumption. In standalone 5G or SA5G, a new inactive state is introduced for more efficient state transition. To infer different RRC states and the transition timers, we use the RRC State Inference tool, RRC probe. In RRC probe, a server sends UDP packets to a UE which will act the incoming packet. The RTT observed by the server depends on the UE's instant RRC state. Take the state machine on the left as an example. If it is actively monitoring the network activities in the connected state, it can respond very fast. But if the UE already turned off its radio and enters the idle state due to inactivity, an ACK won't be sent out until its next wake up. The server varies the intervals between packets to trigger different states and records the RTT. We integrated the RRC probe into our measurement tool, 5G tracker. Using RRC probe, we infer different states and timers for different network settings. We can clearly see from the results that the RTT pattern changes when the packet interval increases over a threshold, which is the UE inactivity timer. For 4G, it is 5 seconds, while for NSA and NSA 5G, they are 10 seconds. By comparing the results of SA and NSA 5G, we find that the UE remains in the new inactive state for about 5 seconds before transitioning to the idle state. This state provides an efficient mechanism for UE's radio to sleep, and at the same time, enables a quick transition back to the connected state. Please refer to the paper for the more detailed results. We further study the impact of state transitions on power consumption. When there is no network traffic, the UE still stays active for a period of time before turning off its radio, demoting to the idle state. This period is called the tail period. We find that 5G consumes more power during the tail period than what used to be experienced over 4G. And the number is especially high for minimum wave 5G. Also, the additional switch from 4G to 5G when the UE promotes to the connected state on the NSA 5G incurs a large amount of power consumption. All this indicate 5G is less efficient in state transitions. Power measurements on modern smartphones is not trivial. Vendors have been making smartphones more closed by integrating the battery and back cover with its main body. Many recent works rely on software API for power readings. To use a hardware monsoon power monitor for more precise measurements, we removed the smartphone battery and reconnected the battery logic board to the monitor. Since the 5G measurements need to be conducted outdoor, the monitor requires an external power supply, so we took a portable power station, and the laptop was also carried to log the readings from the power monitor. In terms of data collection, we conducted both in-the-wild walking experiment and controlled stationary experiments. For the walking experiment, we walked through a loop with several 5G towers. We also have conducted control experiments by hand-holding the smartphone at a fixed location with clear line of sight to a 5G panel. During experiments, we also conducted network-based logs such as downlink and uplink throughput using 5G tracker. From the control experiment where we set different target uplink and downlink throughput for data transfer, we can see the throughput, the power increases linearly as the throughput increases. However, the power of UE on the minimum wave 5G increases at a slower rate. Basically, minimum wave 5G consumes more power than 4G and low band 5G at lower throughputs. But minimum wave 5G becomes more efficient after a certain threshold around 200 megabits per second. Similar conclusions can be found from the uplink transfer results. Minimum wave 5G is more efficient at higher throughput. Signal strength also affects the power consumption. 5G, especially minimum wave 5G, signal strength can fluctuate frequently and widely. To better isolate the impact of signal strength, we divide the throughput from power to calculate the energy efficiency for different signal strength levels. Energy efficiency, or energy per bit, means the average energy consumed to transmit each bit of data. As the signal strength increases, the energy per bit drops. Looking into the power throughput signal strength relationship, we can conclude that both throughput and signal strength can affect UE power. With the network band information recorded by 5G tracker, we also see different bands have varied power characteristics. All these findings motivate us to look for a better way for power modeling. Traditional approaches consider only a single factor, mostly either throughput or signal strength. However, in 5G, multiple factors need to be considered due to the high variability of 5G throughput, the vulnerability of 5G signal to the physical environment, and the diversity of 5G bands. Therefore, we turn to machine learning-based data-driven approaches to take into account multiple factors. Specifically, we use the decision tree regression algorithm. We construct the power model for different devices, different networks, and also different radio technologies and bands. By comparing the mean absolute percentage error averaged across different network settings, our model considering both throughput and signal strength information produces lowest prediction error at 5.4%. Although hardware power monitors can provide precise power readings of mobile devices by directly supplying power to them, it is very inconvenient for users to retrieve such information in daily use. Android exposes battery information such as current and voltage, which can be used to calculate the power. We next study the accuracy of battery status readings by running different activities and measure power using both the software power monitor and the monsoon power monitor, and calculate their relative errors. The results show that the software approach always underestimates power. We also find that a higher sampling rate may help provide better estimation, but this will incur higher energy overhead. Therefore, we apply decision tree regression to calibrate the software power readings. The figure shows the calibration performance at different sampling rates, and the software-based approach can achieve comparable performance with our power model. A higher sampling rate at 10 Hz can even lead to better performance at higher overhead. Now, Arvind will cover the rest.
Thanks, Xumiao. Next, we look at the QoE implications. With the limited understanding of 5G's implications on applications and services, no doubt there is no killer 5G app yet for the masses. Ericsson Mobility Report projects that by 2025, 76% of the mobile traffic will be driven by video content, followed by others. We therefore select video streaming and web browsing as two applications to understand QoE implications of 5G. For video streaming, the automatic video quality selection option, or more generally the adaptive bitrate or ABR algorithm, is one of the primary tools to optimize the quality of experience. If this algorithm works well, they could keep us binging and generate revenue for the content providers. The research community has proposed several ABR algorithms that can be primarily categorized into one of the four groups: buffer-based, throughput-based, control-theoretic, and machine learning-based. In total, we picked 7 state-of-the-art ABR algorithms proposed in the literature and put them to test. We focus on two metrics here: one, bitrate, and second, video stall time. The desired sweet spot is achieved when the bitrate is higher with lesser stall time. For 4G, we find several existing ABR algorithms work well and fall in the sweet spot. For 5G with millimeter wave coverage, most algorithms do well in achieving bitrate, but suffer with the stall time. On average, we find that streaming over 5G increases the stall time by approximately 58% when compared to 4G. There are two main problems causing ABR to suffer in 5G. Number one, many ABR algorithms rely on throughput predictors to make bitrate decision. But the wild and frequent fluctuations in 5G performance degrades the prediction accuracy, leading to non-optimal decisions. Secondly, an ABR algorithm decides the chunk quality based on the information it has, with no ability to roll back once the decision is made. For example, when the throughput is high, the ABR algorithm might select to download the next chunk at the highest quality, only to realize the throughput has suddenly dropped, leading to stalls. In the paper, we propose a simple 5G-aware ABR video streaming strategy which uses a superior throughput predictor to fall back to 4G if 5G performance is predicted to drop. We demonstrate that simple strategies like this can help reduce the stall time without significant loss in quality and at the same time improve energy efficiency. Next, we also consider web browsing application as a case study to understand performance versus energy trade-offs. To do this, we load the top 1500 Alexa websites separately on both 4G and millimeter wave 5G networks. Our analysis shows that 5G provides marginally better performance but comes at the cost of high energy consumption. 4G, on the other hand, uses much lesser power. Therefore, depending upon the radio band and technology, indeed we find a trade-off between performance and energy efficiency. However, challenges lie in deciding which interface to use to load a web page. In the paper, we built simple decision tree-based models for different desired QoE. For instance, if one prefers high performance, the model would select 5G interface for 95% of the websites from the test set. On the other hand, if one prefers better energy saving, the decision flips and selects 4G or LTE interface for 96% of the websites. As a proof of concept, we built several such models for different QoE configurations and reveal interesting insights and results. Coming to the key takeaways, we quantitatively reveal the importance of edge over the end-to-end network performance across different radio technologies, 5G carriers, and deployment modes. We also highlight key challenges in meeting ultra-high throughput demands. In terms of power, we find that due to the complex ecosystem of 5G, there are several factors impacting power and energy efficiency. We also provide key insights into how upper layer applications should best utilize 5G by balancing the critical trade-off between performance and energy efficiency, as well as become 5G aware. Last but not the least, our study also provides motivation and research opportunity to design intelligent radio or band selection schemes that can meet the desired application QoE efficiently. To conclude, in order to reveal the state-of-the-art landscape of the 5G ecosystem, we conducted a comprehensive measurement study of commercial 5G services here in the US from and across three key dimensions: network performance, power, and application QoE. Thank you.